All right, next reaction we're going to talk about is called epoxidation, okay? Again, this is an alkene addition reaction. The reagent most common to use this is MCPBA, all right? And this results, we don't add two different atoms, we add one oxygen atom, and it's connected to both of the carbons, right? And this functional group is called an epoxide. Okay, so it's a pretty simple reaction. We basically just add an oxygen, break the pi bond over here, and there you have your product. All right, now anytime you form these three-membered rings, right, these are always going to be on the same side. Okay, so these are always going to be on the same side of the molecule. They're going to be both B dashes or both B wedges. But this is something that we can kind of understand because a three-membered ring is so small, right? We just need to know that they're always going to be on the same side. So in fact, we don't even have to draw in the stereochemistry here. It's just going to be assumed. So when we have epoxide, we're just going to assume that that O is connected to the same side of the molecule, right? Because three-membered rings are so small, all right? So let's look at the structure of MCPBA. MCPBA stands for meta-chloro-peroxybenzoic acid. MCPBA. Right, as organic chemists, we like keeping things simple, and that means using lots of abbreviations. So MCPBA stands for meta-chloro-peroxybenzoic acid. I'm going to draw the structure of this compound. We have a benzoic acid, a chlorine, and then we have a peroxy group here. So a peroxy group is like a carboxylic acid, but it has an extra O. It has an extra O in the molecule, all right? So what I'm going to do here is I'm just going to simply kind of highlight one of the oxygens in blue because that's the oxygen that's going to add to our alkene, all right? So let me just show you how this mechanism works. It is a one-step mechanism, all right? So we take our double bond, and what we really need to do here is draw our MCPBA molecule, okay? Instead of kind of writing all this out, I'm just going to call that an R group because there's some carbons there, and it just makes it a little easier for us to kind of draw this molecule, all right? The key to the mechanism is drawing our MCPBA molecule in the right way, and it basically folds up on itself as such, where this hydrogen bends around and is near that double bond O. So when we draw it the right way, we can basically look at the mechanism where this double bond is going to form a new bond from the O to H. That causes those electrons to attack that carbon. The pi bond will come back and attack the O, which breaks this bond here, right? Basically adding this oxygen, all right? So after you do this mechanism, we've added this O in blue, okay? We've formed our epoxide, and then the other byproduct we have is O double bond to carbon to OH and R. We've now formed a carboxylic acid group. The carboxylic acid group we don't want, we're going to wash that away. So the main product that we form and that we're interested in making is our epoxide. Okay, so that's the mechanism on how we do our epoxidation. All right, and that's really part A to this reaction, is making our epoxide. Okay, what we're going to do now is we're going to basically be working with that epoxide to form an anti-diol. So we saw we can use osmium tetroxide to form a syn-diol, but we can use epoxidation, we can use an epoxide to form an anti-diol, all right? So when we start from an alkene, this is a two-step process. Step 1, we add MCPBA, that will make the epoxide, right? And we just saw that. And then in step 2, we can either add acid or base to open up the epoxide. Okay? Again, you have to form two stereocenters, or when you form two stereocenters, you want to show the stereochemistry. In the top example, right, we're not forming two stereocenters, so we don't have to show the stereochemistry. But in the bottom example, we have formed two stereocenters, so it's important to show that the two OHs are anti to each other, right? We're making an anti-1,2-diol, all right? So if we kind of break down this bottom reaction here, right, in step 1, we're going to be forming so in step 1, when we add MCPBA, I'm not drawing the mechanism, I'm just drawing the product, right? Again, the product we get out is an epoxide, right? That's what we saw up here. We form our epoxide. And then step 2, when we add acid or base, right, either of these will then open up the epoxide, okay? It will open up the epoxide. So if I ask you to fill out the reagents, just pick one. Write H3O plus or write NaOH. Don't write the whole thing, right? I know either of these can open up the epoxide. And this is sort of akin to what we saw before, right? If we had a chlorine here, right? Remember that chlorine was blocking one face, so our nucleophile had to come in from the opposite side. And that's the same thing here. When we have H3O plus, water will be our nucleophile, NaOH will be our nucleophile, and these are again going to attack from the opposite side on where that O is. The O, 50% is up, dashes, or wedges, and 50% back, dashes. So you're just going to get the opposite stereochemistry. So it's important here to notice, again, just a reminder, we have to have our opposite stereochemistry in this reaction, all right? And here, if you notice, I haven't covered the mechanism. We'll cover this mechanism in the second semester of organic. So we don't have to really worry about the mechanism for this second step here. I'm not going to teach it to you now, nor obviously ask you about it on any sort of assessment we have. All right, so to quickly review, in the epoxidation reaction, right, MCPBA will react with an alkene to form an epoxide. We can then use that epoxide here to form a 1,2, an anti-diol, right? So in this example, because I started with the alkene, I had to have step 1 and then step 2. Right? If I ever started with just the epoxide, right, we would only have to add the acid or the base.